Thank you so much, Nicola, for having me. I'm very happy to be here to tell you a little bit about the ATLAS detector, as well as some of our most recent analyses. So I'll start with a quick outline. I will include a bit of a standard model introduction because I think there was people from the entire physics department that aren't necessarily high energy physics, so I hope the HEP folks aren't too bored by the introduction. I'll also give a bit of a detailed introduction to the ATLAS and LHC, and then I'll present some recent results with an emphasis on novel techniques. So here I've included some analysis that are new in ATLAS or that have some interesting data analysis techniques. So this includes searches for di-Higgs bosons, our recent searches for leptoquarks, as well as some recent searches that we have for dark matter. Okay, so let me start off with a quote by Michelson in 1903, who said, "The most important fundamental laws and facts of physical sciences have all been discovered." Now, Michelson had every reason to think that. We went from 400 BC and thinking the world was made of 4 elements to 1870 when we had discovered the entire periodic table. And of course, he was wrong, fortunately, and in 1910, we discovered that the periodic table are made of atoms. And within atoms, we have nuclei, and within nuclei, we have protons and neutrons. And in the 1960s, we discovered that even these protons and neutrons are made of substituents called quarks. And these quarks made it into what is today known as the standard model. So we have 6 different types of quarks shown in the purple here. And we also have what is known as leptons. So the electron being the original lepton, which was the guy that circled the atom. And then afterwards, we also found its partner particles, the muon and tau, as well as the respective neutrinos. Now, our understanding of forces underwent a dramatic change as well. So we went from 1660 to knowing about gravity, to 1860 understanding the electromagnetic force, to 1970 and understanding that what keeps the quarks bound inside the protons and neutrons is the strong force. And we also had the weak force, which basically mediates interactions within the sun. And we also found that we had other particles called bosons that mediate each of these force interactions, with the gluon particle mediating the strong interactions, the photon mediating the electromagnetic interactions, and the Z and W bosons mediating the weak interactions. We still haven't found a particle that mediates gravity in the standard model. Now, the standard model was, let's say, more completed with the discovery of the Higgs boson in 2012, for which a Nobel Prize was received. So this is the complete standard model together with the Higgs boson that was found. And just to emphasize that finding the Higgs boson was hard work. It was really like looking for a needle in a haystack. So if on this plot, for example, on the vertical axis, you have the total number of events that are produced in a collider. And on the horizontal axis, you have the square root of energy at which a collider runs. So the Large Hadron Collider, which runs at around 14 TeV, is at this green line here. So you can see the total events produced at the LHC are 10 to the 8 events every single second. The number of Higgs events, on the other hand, are 10 to the -2 events per second. So there's a 10 to the 10 order of magnitude difference between the total events that the LHC produces and the number of Higgs bosons. So it really was hard work in order to sift through all these junk events in order for us to find the Higgs boson. However, as Albert Einstein said, the more I learn, the more I realize how much I don't know. So what don't we know? What doesn't the standard model explain? Well, according to the standard model, neutrinos shouldn't have mass, but we found in other experiments that they do. The standard model also doesn't describe the abundance of dark matter in our universe. It doesn't describe how gravity fits into it. And it fails to describe several anomalous experimental measurements, such as B anomalies and the muon magnetic moment, as well as others. So in order to address these shortcomings of the standard model, we can do one of 2 things. We can very precisely try and measure standard model properties in order to search for deviations from the standard model. Or we can search for some sort of beyond standard model theories with explanations. So how do we go about searching for these remaining questions? Well, as William Deming said, "In God we trust, all others must bring data." And our data comes to us basically in the form, we have to basically use a time machine to go back until shortly after the Big Bang, when particles loosely existed in the universe, and then take a magnifying glass and look closely at how these particles are interacting. And basically what will serve as our time machine is the Large Hadron Collider, and each of our detectors around the Large Hadron Collider is going to be like our magnifying glass. So at the Large Hadron Collider, it's a 27-kilometer ring we have at the border of Switzerland and France. We collide protons, so there's that go in each opposite direction. And we have 4 different interaction points. So one of them is at the CMS detector, another one is at the ATLAS detector, and then the other 2 are the LHCb and ATLAS. And all of them look for different types for physics, let's say, except ATLAS and CMS, they look for similar features. Now, just to emphasize, the LHC doesn't take one proton and another proton and collides it. It actually takes 10 to the 11 protons in each bunch and another 10 to the 11 protons, and it collides all these protons every 25 nanoseconds. And this large number of proton collisions also gives us a large number of interactions in each of these bunch crossings. And this is what's known as pileup. So we have to take different mitigations to reduce pileup in order to find our interesting events like the Higgs boson or exotic particles. So just to give you an idea, the plot on the lower left-hand side is the mean number of these interactions per bunch crossing. And if you look at the purple area, you can see that for all the years we've been running, this mean number is about 30, but it goes up to as high as 70. So it is quite a challenge getting to the interesting events and reducing this pileup. So you can see that, you know, our challenge is more than just looking for a needle in a haystack. It really is like looking for a needle in a haystack in a battlefield. So the LHC gives us a 40 megahertz bunch rate crossing, but we can only save 1 kilohertz to tape. And our interesting physics events are rare. So what we do is we use the ATLAS detector in order to search for these interesting physics events. And the way the ATLAS detector works is each different layer of the ATLAS detector uses a different technology in order to detect different standard model particles. So this is a zoom in of the ATLAS detector. And this is it's about 40 tons, I think, and this is its cross-sectional view. So starting with the innermost layer, so the innermost layer is called the inner detector and consists of 12 different layers that are surrounded by a magnetic field. And when particles travel in these layers, what happens is they are bent by the magnetic field. And because we know the magnitude of the magnetic field and the curvature of the bending, we can infer the momentum of the charged particles. So this inner detector is used to reconstruct what are called tracks and give us their momentum and charge. And that works for all the charged particles of the standard model, which are the ones I've highlighted on the left here. Now, the inner detector consists of the innermost layer. It's a semiconductor pixel detector, followed by a strip semiconductor detector, and finally a transition radiation detector, which is basically tubes filled with gas. And when particles travel through it, they ionize the gas. The bottom here is a picture of the inside detector. The next layer is the electromagnetic calorimeter, and this absorbs electromagnetically decaying particles, so primary electrons and photons. Now, it doesn't just detect a single electron and photons. What happens is these electrons and photons cascade into a series of other electromagnetically decaying particles to give us what are known as electromagnetic showers. So our electromagnetic calorimeter actually measures these electromagnetic showers. And the technology we use is what's called a liquid argon calorimeter. So basically, this layer of the detector consists of alternating zigzag metal pieces that are separated from each other by these rigid honeycomb layers, and they are set in the liquid argon. So as particles transverse the detector, the liquid argon is ionized, and the resulting free electrons are collected on these metal plates. The next layer of the detector is the hadronic calorimeter, and this basically absorbs hadrons, which are things like protons and neutrons and other particles that consists of quarks. Now, again, it doesn't just detect single quarks, single hadrons. These hadrons interact with the detector. They create what are known as hadronic showers. So the detector detects these hadronic showers, which we call jets. The technology that we use in ATLAS for this is lead and scintillating tiles. It's known as the tile calorimeter. And what happens is there's alternating layers of lead and scintillating tiles. So as hadrons travel through them, the hadronic showers are initiated in the lead, and the resulting freed photons are detected by the scintillating tiles, which are then read out by photomultiplier tubes. And that's how we detect the energy of these hadronic showers. And on the lower left-hand side picture is just a picture of the tile calorimeter, one of the end caps being inserted into ATLAS. The very last layer of the ATLAS detector is the muon detector. Now, muons escape the detector, but they leave tracks in the muon spectrometer, which are the very last layer. And the technologies that we use in ATLAS for the muon detector are 4 different technologies. So they're thin gap chambers, cathode strip chambers, monitor drift tubes, and resistor plate chambers. They're just basically different combinations of either metal plates or plates with wires across which an electric field is applied. And there's gas in these chambers such that particles ionize the gas, leaving tracks in these chambers. Finally, neutrinos escape the detector, but their presence can be inferred from the presence of missing transverse energy. And the basic principle is, in the Z plane where the protons collide before the collision, the sum of momenta in the transverse plane of the detector is 0. So by conservation of energy, it must be true that after the collision, the sum of the momenta in the transverse plane should be 0. If it's not 0, it means either there's a neutrino that left the detector undetected, or there's some exotic particle such as dark matter that we haven't detected. So missing transverse energy can be used to infer the presence of neutrinos or exotic particles. Okay, so that's basically how the ATLAS detector builds a picture of all the different particles in the events. But I still haven't described exactly how does it sort through all the different junk to find important events. So how does it get rid of all the overlapping interactions to get to our important events? Well, it uses a trigger system. Now, our trigger system has a multi-step approach. So in order, this is an example of a picture the ATLAS detector takes. And in order to fully reconstruct all the energy deposits within this picture, there's a multi-step process. So the first step is what we call the level 1 trigger. It is a hardware-based trigger that basically consists of electronics on the calorimeter and the muon detector. So these electronics at the hardware level, they do a very quick and coarse granular sum of the energy deposits in the calorimeter and the muon detector. So they build this very blurry picture of where our energy is in the calorimeter. And based on this picture, this level 1 trigger decides which events to retain and which events to throw out. And by doing this, it reduces the 40 megahertz LHC collision rate to about 100 kilohertz in about 2.5 microseconds. The next level is a higher level trigger. Now, this is a trigger that runs in software, and it has 2 steps. So the first steps of the higher level trigger is it takes the events passed by the level 1 trigger, and then it looks at what we call regions of interest. So these are interesting regions of the detector where we have a lot of energy deposits. And for these regions of interest only, the higher level trigger builds a more fine granular image of the detector. So it gets more fine granular energy sums. And based on this, it decides whether to retain or throw out events. If it decides to retain the events, then the final full picture is reconstructed with the full granularity and all the subsystems. And the higher level trigger with these 2 steps that I just described can then reduce the rate from 100 kilohertz to 1 kilohertz in about 0.2 seconds. And then these 1 kilohertz of data are saved to our tape for further physics analysis. Okay, so I've told you a little bit about how the ATLAS detector works. Now I want to talk a little bit about some recent results of the ATLAS detector with an emphasis on novel techniques. So the first analysis that I'll describe a little bit is Dihiggs searches. Now, why are Dihiggs searches interesting? Well, I said at the beginning of the talk that a good way for us to try and look for remaining mysteries that the standard model doesn't address is by measuring standard model processes and looking for deviations from the standard model, or by searching for exotic particles. And the Dihiggs searches are a really nice tool that allow us to do both. So Dihiggs, measuring the process of two Higgs bosons being produced, will allow us to one day verify in detail how accurately we have described this in the standard model, but it'll also allow us to search for extra particles that could be produced through this process. Now, this is a very difficult process to measure. So producing two Higgs boson, this production is several orders of magnitude lower than signal Higgs production. And what makes it even more difficult is there's destructive interference amongst diagrams that make it even smaller. So we can produce two Higgs bosons with this diagram on the left or this diagram on the right, but they destructively interfere. So the total production rate of two Higgs bosons is even lower than each one individually. However, Dihiggs production can be enhanced by many beyond standard model theories. So there can be some exotic particle X, and it exists in many different theories, and it can basically decay to two Higgs bosons. So we can place limits on these exotic particles by looking for two Higgs bosons. We can also have what's known as non-resonant production, which means the Higgs coupling to either the top or bottom quarks, as in the diagram on the left, or to itself, as in the middle diagram, can be modified with respect to the standard model values. So if we measure this coupling precisely, we can also see if there's deviations from the standard model that could indicate exotic particles. Now, the two Higgs bosons that we create, they can decay to a variety of different things. So on the lower left-hand side are all the different decay modes. They can decay to B quarks, Ws, taus, Zs, or photons. And within the ATLAS detector, we look for Dihiggs searches in many of these channels. And the one I will focus on today is the one where one Higgs decays to two B quarks, and the other Higgs decays to two tau leptons, which happens about 7.4% of the time. And my reason on the focus for this channel is because it's a recent result, and again, it uses some techniques that we haven't widely announced before. Okay, so let's look for Higgs bosons in this channel. So we can have basically two different types of signatures. So when we have two Higgs produced, either through the production of this exotic particle X or on its own, one Higgs decays to two B quarks and the other one decays to two leptons. And if the Higgs are very boosted, if they have a lot of transverse momentum, what happens is their decay products become very well common eliminated. So they are very close together. So these resulting B quarks or tau leptons are very close together. This is known as the boosted channel. If, on the other hand, the two Higgs bosons aren't boosted, they have lower transverse momentum, their decay products, so the B quarks and the tau leptons, are well separated. Now, for this channel, we're looking at the hadronically decaying parts of the B quarks and the tau leptons. And when things are well separated for the non-boosted case, we can very easily reconstruct these B quarks and these tau leptons because we use small radius jets. On the other hand, if the decay products are well collimated, these small radius jets, which usually have a radius of 0.4, they're going to overlap. And because they overlap, it's going to be very difficult to know that we have two B quarks or we have two tau leptons. So our standard reconstruction techniques using these regular radius equals 0.4 jets don't work. So we have to use different reconstruction techniques. So what we use instead are reconstruct larger jets. So these are radius equals 1 jets in order to look at the boosted channels. Now, for the next few slides, I'm going to focus on the boosted channel, again, because it's our most recent result and contain some new techniques. So I said that we're going to use large radius jets in order to identify our collimated decay products from the Higgs bosons. So what is the exact recipe that we use? So let's look at first the decay of the Higgs to B quarks. So first we take a large radius jet and we remove all the low energy components from the jet. So we remove all the things that come from pileup. This is a process known as trimming. Next, we build 2 small radius jets, and we build these from basically the tracks in the inner detector. And we B-tag these tracks. So we see whether they come from B quarks depending on where in the inner detector they decayed. And then we match these track jets to the fat jets. And finally, we select a mass window around the Higgs mass to make sure that our fat jet really came from a Higgs boson. So that's how we identify a Higgs coming from 2 B quarks. Now let's look at the opposite end. How do we identify a Higgs going into 2 taus? Well, these 2 taus, we're looking at the hadronic decay. So they typically decay to pions and neutrinos. And these pions have a characteristic number of tracks that they leave behind in the inner detector. So our recipe here is, again, we take a large radius jet with a lot of deposits in the calorimeters. We identify 2 small energy jet, 2 small radius jets within the big jet. Then we match tracks to these small radius subjects that probably come from the pion decay. And finally, we use a boosted decision tree algorithm in order to distinguish between these di-tau signatures and multi-jet background. Now, this boosted decision tree algorithm exploits the fact that for multi-jet backgrounds and for di-tau signals, we will have different shower shapes, as well as we will have a different number of tracks. So this is sort of a novel technique that we've used in ATLAS, this di-tau identification. And you can see that its reconstruction efficiency is much better than with standard reconstruction techniques. So if you look at the plot on the left, this is the efficiency of reconstructing these boosted 2 tau leptons as a function of the di-tau momentum. So the standard algorithms are shown in red, and you can see that the efficiency of the algorithm goes down significantly as our momentum of the di-taus increases. And this new way of identifying di-taus is shown in the black. So you can see the efficiency is quite high with high energy of di-tau PT. Okay, so these are the results. So employing these sort of novel reconstruction techniques, these are the results that we get. So on the top left-hand plot shows first what kind of background events we expect. So if we look at the mass of the 2 Higgs system, we can see the backgrounds by the different colors. The most prominent backgrounds are the things shown in turquoise. They come from Z decaying to 2 taus. If we had a signal of an exotic particle X decaying to 2 Higgs bosons, we would see it as these dotted lines. And our data is just these 2, this data point with this large uncertainty on it. We've basically just so far identified 2 events that could be di-Higgs candidates, but hopefully we will increase these statistics on this with the future runs. So on the lower left-hand side, this is a picture of one of our di-Higgs boson events candidates. So you can see we have one jet that is large radius on one hand side that probably comes from the B quarks, and on the opposite side we have another one from di-taus. So what we can do is we can put the limits on the cross-section times the branching ratio of this exotic particle X, which is basically a heavy narrow scalar resonance decaying into a pair of Higgs bosons. And this can come from things like 2 Higgs doublet models, for example. So we can put a limit on the cross-section times branching ratio as a function of the mass of the particle. So typically the way to read the ATLAS limits plots is the dotted line is the expected limit. The green band is the 1 sigma error around the expected. The yellow band is the 2 sigma error around bound, the expected, and then the overlapping data points are the black points here. So this is the limits that we extract. Okay, so changing gear a little bit into another set of results. So recently, the searches for particles known as leptoquarks have become very popular. So recently, ATLAS has given sort of a big push towards trying to find leptoquarks in a variety of search channels. And here I'm going to show you one of the big motivations for that. So one of the big motivations driving this revived interest is measurements such as this one, where we measure a B hydron decaying to a D star. And basically what happens in this process is a B quark changes to a C quark. In the process emits a W, and the W can then decay to a tau or a neutrino, or a muon or a neutrino. So several experiments measure the ratio of the tau decays over the ratio of the muon decays. And what several different experiments see are deviations from the standard model. And that you can see on the right-hand plot here. So the standard model expectation is the thing shown by the green line. Now, experiments such as VEBAR, which is shown in the blue, you can see show a deviation from the standard model. Experiments at Bell, which is the next 3 line, also show deviations from the standard model. And finally, most recently, experiments at LHCb, analyses at LHCb also show some deviation of the standard model. So these are 3 different detectors running under drastically different conditions that all show 2 to 3 sigma deviations in this measured ratio. A naive combination of these results gives you about a 4.1 sigma deviation from the standard model. So the reason leptoquarks are interesting is because they're a unique type of particle that is the only one that can couple to both leptons and quarks and provide an explanation for these anomalous measurements. So you can imagine if you look at the middle diagram here, if you had a leptoquark produced in this type of interaction that couples on the one hand to B quarks and taus and muons, and on the other hand to neutrinos and C quarks, you could explain these deviations from the standard model. Another reason these particles called leptoquarks are interesting is because they could also explain outstanding deviations in the measurement of the muon magnetic moment. So in the standard model, the muon magnetic moment is described by the Feynman diagram that you see on the bottom hand here. So it's basically a muon and with a photon that changes to a quark with a photon emitted. This is known as the G-2 mu measurement, and it has long outstanding deviations. And you can imagine if there was a leptoquark that couples both to quarks and to muons, it could explain the deviations here as well. So as I said, ATLAS has recently embarked upon a rich program looking for leptoquarks. So this is just one example of the types of processes that we're looking for. We basically look for an interaction where we have 2 leptoquarks created. Each leptoquark then decays to a top quark and an electron or a muon. The top quark subsequently decays to Ws, which then decay hadronically. So the result here is from the Ws is going to be 2 large radius jets. Okay, so I've mentioned the leptoquark signature is going to be 2 large radius jets, and it's also going to be accompanied by 2 leptons. Now, it can be sometimes difficult to separate this leptoquark process from its standard model backgrounds. And the main standard model backgrounds are known as top events. So that's the one that you see in the middle here. Top events produce a very similar signature. So they also have 2 jets on either side of the detector, and they also have 2 leptons on another side of the detector. But what's different about these top events is they also have missing transverse energy, which we don't see in the leptoquark case. So we can use the presence of missing transverse energy to differentiate the top events from the leptoquarks. Another significant background to this search is what we call Z plus jets events. So again, in this case, we have two jets that are created on either side of the detector. And we also have two leptons from the Z decays. But in this case, the leptons are on the same side of the detector. So we can exploit this fact to differentiate our leptoquark signal from our Z plus jets. So using these two features of differentiation of the background from the signal, we can define control regions. And these control regions are very rich in our top events as well as in our Z-jets background events. And we can use these control regions in order to normalize our top and Z-jets background. So it is very often that our Monte Carlo is not perfectly modeled. So if we look at a representative control region, such as the one showed by the diagram, we could very well have a case where, for example, for our top events, the Monte Carlo shown in the green here doesn't quite match the data that is shown by the dotted lines. So what we do is we perform a fit in these control regions, and we scale the Monte Carlo up to the data, and we derive a scaling factor. And the scaling factor we can then use to scale the same background in the signal region. So we perform this scaling, we extract a scaling factor that's known as mu top, for example. In this specific analysis, the control region is shown on the lower left-hand side here. The discriminating variable that we use is a boosted decision tree, and we use it in order to classify signal and background events. The boosted decision tree exploits features like the mass and the momentum of the leptons, as well as the mass of the jets and the leptoquarks, as well as the jet substructure. So we can see this is the control region plot of the boosted decision tree score. And we can normalize the data to the Monte Carlo here to extract this normalization factor. Then we can go to a signal region, which is a region that has a lot of our signal in it. And we can apply this normalization factor to the top events in the signal region. So in the left-hand plots here, these last three bins are our signal region. They basically correspond to different scores in the BDT distribution. And the top and the Z-jets background here are normalized from their respective control regions. The first two bins are the respective control regions themselves. So the top on the left and the Z-jets in the middle there. So using these different regions, then again, we can place limits on leptoquark searches. So on the left-hand side, we have the limit on the leptoquarks decaying to top and electrons. On the right-hand side, we have limits on leptoquarks decaying to top and muons. So again, the black dotted line is the expected limit, surrounded by the 1 and 2 sigma error bands. And this smooth black line is the data points. If a leptoquark signal were to exist, it would be represented by this red line. And because we don't see it up to a leptoquark mass of about 1500 GeV, we can basically exclude everything to the left of this line. So we exclude leptoquarks that are higher than about 1500 GeV for both the electron case and the muon case. Okay, so the last search that I'll tell you a little bit about is dark matter searches. So again, this is an area in which ATLAS looks for a lot of different types of dark matter in a lot of different types of channels. And the reason that there's such a heavy emphasis on dark matter is because astrophysical observations show us that 85% of the universe's matter contact is in fact dark matter, and we basically have no idea what this stuff is. So at the LHC, we have to assume that our dark matter somehow couples to standard model particles. Without this assumption, there's basically no way of us detecting it. So we assume it couples to the standard model, and we also assume that it's produced in association with the standard model particle. So the way that it would look in the ATLAS detector, if again you look at the transverse view of the ATLAS detector, is you would have the standard model particle coming out of the detector in one direction, and the dark matter particle would escape the detector in the opposite direction, but it would not be detected because it interacts very weakly with the detector. We know dark matter interacts weakly from astrophysical observations. So the only way that we can detect it in ATLAS is by inferring its presence by looking for missing transverse energy. So there's a few approaches for dark matter searches at the Large Hadron Collider. There are first what is known as simplified models. So these are very basic benchmark models, and they have a very simplified mediator. We basically here look for missing transverse energy with some standard model particle in the final states. So we can assume that these standard model mediators are either regular standard model particles that we know about. So we have some standard model particles, we have a regular Higgs or Z produced, and this Higgs or Z then decays to standard model. Or we can think that this mediator between the standard model and dark matter is some exotic particle, so some scalar or vector particle that we haven't yet discovered. And then we can assume that this exotic particle decays to dark matter. So that's what concerns simplified models. We look for very generic missing transverse energy plus X final states. And then we can also form more complete models. So these are fully theoretically developed models. And here the final states aren't just missing transverse energy plus some X particle. Here the final states really depend on your model assumptions. So an example of such a complete model is supersymmetry, for example, for which I put a representative diagram. And with this thin supersymmetry, we have a weakly interacting particle known as the neutralino, which is a natural candidate for dark matter. So these are two approaches for dark matter searches at the LHC. I'm going to describe an analysis that uses the simplified models to search for dark matter. So I'm going to, again, describe one of our most recent analyses. So this recent analysis assumed that we have some particle Z prime produced, and this particle then decays to dark matter, which is produced on one side of the detector, and another pseudoscalar particle called A or S, which then subsequently decays to W or Z bosons, and the W and Z bosons then hadronically decay. Now, at very high momentum, the hadronic decays of this W and Z are again very collimated, which means they're merged. So again, we're going to need special objects to identify this because our standard reconstruction techniques are not going to be efficient here. Now, this merging is going to bring us really close to the granularity limits of the calorimeter. So what we will do is we will use angular track information in order to improve the spatial resolution of our objects. So we define what are known as track-assisted reclustered jets in order to define jets, but that take advantage of the good resolution of tracks. So I'll describe how that works in the following slides. So in order to build these jets, we first identified two small radius jets where our W and Z bosons were. Next, we recluster the inputs from these jets into one large radius jet, where the radius this time is 0.8. We then remove the soft components of the jet that are probably from pileup, again through a process known as trimming. After that, we look for tracks that match to the small radius jets. And then we rescale the tracks to the momentum of the small radius jets. So we take the tracks and we recalculate their momentum. So the new track momentum is the old track momentum, but with a rescaling of the momentum from the calorimeter jets. So this quantity basically gives you a nice mixture of calorimeter information and tracking information to optimize the information that you have. And then what you can do is you can calculate the properties of your jets from the tracks themselves. Again, to give you a bit of a better resolution, because the calorimeter has worse resolution than the tracker. Okay, so using this technique, you can define your control regions and your signal regions and differentiate them from one another. So the main background to this type of analysis are events in which we have Z decaying to neutrinos in jets, as well as events where we have W plus jets. So we define two different control regions from which we normalize these two backgrounds to the signal region. So the first control region is the one in the middle here. So this is a 1 muon control region. And you can see we have a lot of W plus jets events here that is represented by the blue. And we can have another 2 lepton control region, which is on the right-hand side here. So here we mostly have Z plus jets events. So using these two control regions and the technique I described previously, we normalize our background in the signal region, which is the one defined on the left-hand side of this plot. And the signal region has 3 different bins. So the first bin is what we call the merged category. So this is basically where we have one track associated recluster jet, so one tar jet, and this jet encompasses all the energy of both W and Z bosons, and the jet's energy is offset by the missing transverse energy on the other side. So if we then look at the mass of this giant jet, we can look at the distribution here. So you can see that the signal, which is shown in the red, is very nicely separated from the background, most of which comes from top events that are shown in the green and diboson events that are shown in the orange here. We can define another bin of the signal region. It's called a merged region, and it's very similar to the previous region. So again, both the vector bosons are encompassed in this large jet. There's also missing transverse energy offsetting it, but in this case, the missing transverse energy is lower. So it's between 300 to 500 GeV. And again, if we graph the mass of this jet, as is shown by the plot, you can see the signal in the red is again relatively nicely separated from all the different backgrounds, which are in the different colors. And finally, we can have an intermediate signal region. And here, the tar jet encompasses only a fraction of the W and Z energy. And then the rest of the WZ energy is floating somewhere around this tar jet. So it's probably in a small radius jet around the main jet. So we require a tar jet as well as another small energy jet, again, offset by missing transverse energy. And if you look at the mass of the tar jet, again, you can see the signal in the red and the backgrounds in the different colors. So it shows an okay separation, not as sensitive as the previous signal regions though. And again, based on this, we can place limits on our dark matter particle cross-section production times branching ratio as a function of the mass of this particle S from which the dark matter comes from. And again, the expected points are the dotted black line, and the observed is the red line here. There's no significant excesses found for this dark matter search either. Okay, so I hope that I presented to you a quick introduction to the standard model, the ATLAS and LHC. I've showed you some recent results because we don't have any discoveries to brag about. I've tried to focus a little bit on emphasis that we recently discovered that concern novel techniques. So in that regard, I've tried to present more recent searches for di-Higgs bosons, leptoquarks, and dark matter. And well, we unfortunately haven't found any excesses yet. There's more data coming, so stay tuned.